Okay. So this is roughly class 23 of operations research. We're now switching subjects. I'm not going to go into more detail on traveling salesmen and other problems like that because there seems to be a large contingent of people here who've seen stuff like that in the CS class. It's in the book. If you want to, I'm happy to discuss it more in this class. But for now, I think I'm going to shift to fixed point theorems. Okay. How many of you have seen a lot on fixed point theorems? Okay, good. Just one person or two people. Okay, sorry, two people. So it's like this. I don't mind boring two people too much. Anybody want to tell me what a fixed point theorem is? We've got two people who just said they've seen it. This is the most basic question I can ask. Yes? Yes?
So it's like a value such that if you take the function again at that value, you get the same value.
Good. So basically, ready? Oh, almost. I didn't want to hit the people either in front of you or behind you. So fixed point theorems. Given f, find x such that f of x equals x, such x called fixed points. So whenever you get a result, the first thing you want to ask is, let's look at some kind of extreme cases. Does every function have a fixed point? Okay, what's a function that doesn't have a fixed point? X plus 5. I was thinking x plus 1701, but. That's close enough. No, it's when Yale was founded. Yale University, Starfleet Academy, Vulcan Science Institute, the three biggies. Right, this is the little three here, right? Williams, Wellesley, and some other school. Is there any fixed point for this? Is there any x which is unchanged when we add 1701? Can everybody think of a candidate x? There is one possible candidate. Infinity. So depending on where we define this, if you in some sense extend this, infinity would be a fixed point. So you have to be very careful as to what is your space. So what's nice about this simple example is it shows that there will be functions that do not have fixed points. What conditions must we impose to assume that there's a fixed point? How can knowing fixed points help us? How many times are you trying to solve f of x equals x? Are you trying to solve that most of the time when you're trying to solve an equation, or is your equation a little bit different? You might be trying to solve f of x equals a, right? You want to know where this function takes on a specific value, not where it equals itself. Let's introduce a new function. G of x equals the following. I think it's f of x minus a plus x. If g of x equals x, then what can we immediately deduce? Then f of x equals a. So really, trying to solve f of x equals a is equivalent to trying to find a fixed point of a new function g. I don't think this is a great name for the function. What would be a better name for this function than g?
F prime.
Not f prime, because as soon as I see f prime, I think of a derivative.
F tilde.
You could do f tilde that's somehow related to f, or maybe put a subscript a to say that this is coming from shifting by a, or I want it to equal a. If you're only looking at just one shift or one function at a time, it doesn't really make much of a difference. But if you have a lot of things going on, it can become very confusing to keep track of where all these derived functions are. So I would call it either g of a or maybe f sub a. Okay? It's fine to call it g of x, but this way it's really highlighting what's going on. I think probably using g of a, replacing that with f of a, is probably the best notation for something like this. How many of you have heard of the Coffee Cup Theorem? All right, what's the Coffee Cup Theorem?
Are you talking about Brouwer's fixed point?
Yes.
So basically, any continuous function, or should I talk about it
No, continuous function is fine.
Continuous function from a convex compact set to itself yields at least one fixed point.
Excellent. Ready? Oh, sorry. Oh, that was my fault. That was my fault. The room, I think, is slanted. So there were a lot of key words in that. Continuous function, compact set to compact set, and at least one fixed point. There could be multiple. It's often said if you have a cup of coffee and if you stir it, at least one point of the coffee returns to where it started. Whenever you have something like this, you always want to say, what would happen if I remove some assumptions? Is it still going to be true? The other coffee cup theorem is urdish, that a mathematician is just a device to convert coffee to theorems. Okay? We started with a fun problem to motivate linear programming. We started with a chess problem, and some of you, I think, have expressed interest when your semesters become less hectic than they are now to see exactly how far we can push the queen-pawn game. We have an n by n board, we put down n queens, and we want to put down the n queens in such a way as to maximize the number of pawns that can be safely placed. Right? I want to do a similar one to motivate fixed point theorems. This is not going to give us a proof in full generality. So depending on what assumptions we put on F, depending on what space we look at, some fixed point theorems are easier to prove than others. What I'm going to show you has a really nice mathematical technique behind it. And it will be useful for proving fixed point theorems in some settings, but it's also useful for a variety of problems. All right. Ideally, I would have zombies, but I will do Vulcans instead. So let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4. Okay, so we have a 5 by 5 board. And what I want to do is I want to infect squares. And if you have two neighbors that are infected, you become infected. So this would be like the zombie formulation. Once you become a zombie, you always stay a zombie. Once you become a Vulcan, you always stay a Vulcan. You never go back to this emotional state. Okay? What do we mean by sharing? What do we mean by neighbors? Diagonal doesn't count. You have to share a side. Okay? So imagine I have an n by n board. I infect m equals m of n squares. And I see how the virus propagates. Or I see how the teachings of Sirac propagate. Okay? It's disrespectful to smile at Sirac. Can anybody give me an initial configuration of infected cells that will guarantee that everyone is infected? Thank you. Right? The smart-ass answer. Right? If everybody's infected, everybody's infected. So if infect n squared, all infected. This is highly inefficient. Can we do better than n squared? I don't want to do too much better, but can someone do a little bit better? So 1 is n squared minus 1. Right? Because if we have everything but, say, one of these squares infected, it's got so much infection around it, even if it's in a corner, it'll still have two neighbors. So unfortunately, in the limit, if you look at what you have, n squared minus 1, versus what we had before, n squared, in the limit as n goes to infinity, it's still the same percentage. It's 100% of the n squared cells. So n squared and n squared minus 1 in the limit are both infecting 100%. Can you do better? I'm sorry? How do you do n squared over 2? Excellent. So do the checkerboard. If, say, checkerboard white, we do n squared over 2. No. What we're doing is we're doing every other one. Here, here, here. Right. It's not n over 2 squared. Yes.
You just the leftmost column and just the topmost row.
So what you're saying now is you're saying go all the way down and all the way over. So this is your suggestion? Well, okay, but even if we can, this would still be breaking a barrier. It's not as good as breaking the warp barrier, but it's still good. Why would this be good?
Order 2n now.
It's order 2n now. Did you get one yet? Yes. So, if I had done it the other way, I could have do the L. If you do this, takes 2n minus 1. So now in the limit, this is 0%. So let's see what happens. So now if we do this, this becomes infected, right? And then the next moment, nothing else gets infected immediately. Then these two would get infected, right? Then these three would get infected. Okay, technically, how would we prove this? We would use induction, okay. So we'll assume we've proved it by induction. All right, so I've heard rattlings that there's a better way to do it than doing the L. Although the L already gets us to linear, which is much better than what we had. What's better? Long diagonal. So the main diagonal, that takes n. So my question is it possible to do it in fewer than n? Yes.
Can we do just one corner?
Okay, so how would you want to do it? So we've got a 5 by 5 board.
So you can infect just right or down?
As long as you share 2 walls with infected people, you will become infected. So one thing is, when you have a problem like this, what should you do to build intuition? How should you build intuition? What's the first thing you should try? Try smaller cases, right? If we try the 1 by 1 case, it's not that bad. If we don't infect anybody, the infection is not going to spread. If we try the 2 by 2 case, we can only infect 1 square. By symmetry, how many places are there to try? 1. And we see the infection does not spread. Let's try the 3 by 3 case. Now we want to infect 2. Up to symmetry, how many ways are there now? We've done this before. 3. Why 3?
The middle, one of the crosses.
So that's the first move. For the first square that we choose, there's 3 ways. And then when we analyzed tic-tac-toe, we saw that there were 12 possibilities. So up to symmetry, there's 12 cases. 12 cases isn't too bad. And you can just go through and you can brute force the 12 cases, and you'll see that none of them will lead to the infection spreading. Okay? Yes?
How many moves are we doing?
We're trying to do it. We know that if we have n infected cells, everybody will be infected, if we infect the main diagonal. So if we're intelligent, we can infect everybody with n. We're trying to see, is there a clever choice of n minus 1 that will work?
Is it the same as tic-tac-toe? Because one of the 2 moves.
So, right, so it's the same as how many opening pairs of moves are there in tic-tac-toe?
Oh, there's 12 pairs.
There's 12 pairs. So for instance, if we go here and here, that's the same as going here and here. So we're not counting a difference in that. So you can go through the 12 cases. You can also try to figure out, well, what would happen? If we put something in the middle, then when we try to go, where else could we go? And try to see, is there a way to spread? So you can start doing the analysis, and I'll let you play with that. There's a very simple way to prove that the infection can spread to everyone. So how many of you have ever heard the phrase an invariant? Okay, what's an invariant?
It's just something you can say about
that doesn't change. So if we are looking at the discriminant of a polynomial, let's say we have a quadratic. The discriminant is r1 minus r2 squared, right? The difference between the roots. If I shift all the roots by 5, does that change the discriminant? No, the discriminant is invariant under translation of roots. If I rescale the roots by a factor of 5, does that change the discriminant? Yes. So the discriminant would depend on rescaling the roots, but it would not depend on translating the roots. This is one of the reasons why the discriminant is such a nice quantity to study. It's invariant under translations. So we've seen invariance before. We're going to try to see monoinvariance. Or actually monovariance. Anybody want to guess just from the terminology what a monovariant is?
Only one thing changes?
Good guess, but there's only one thing we're studying. So we're studying a quantity, and we will say the quantity itself is a monovariant if something holds. What do you want to assume about the quantity that's going to be the monovariant? What do you want to assume about how it changes? It only changes. One possibility is it only changes once. That's a good possibility, but that's not the definition of monovariant. It only changes in one way. So again, we can define whatever we want. It's what's going to be a useful definition. Monovariants only change in one direction. And what we're going to do is we're going to associate a monovariant to this quantity. And we're going to associate the perimeter of the infection. And the claim is the perimeter never increases. So let's assume the claim for now. We'll prove it in a moment. If the perimeter never increases, what is the maximum perimeter if you have n minus 1 infected? What would be the maximum perimeter?
How are we defining the perimeter?
The perimeter is, so if this is my infection, the perimeter is the outside walls of the infection. So here it would be, this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the perimeter of this infection would be 10.
What if you have just two disjoint pieces?
So if you had two disjoint pieces, so if we add this one over here, 10, 11, 12, 13, 14. So what would we say is the maximum perimeter, the maximum possible perimeter, if n minus 1 squares are infected? 4 times n minus 1. Or 4n minus 4. If everything were infected, what would the perimeter of the infection be? 4n. So if we can show that the perimeter never increases, we know we can't have everything infected. There's got to be at least one cell that's not infected. Right? So is everyone convinced that if we can prove this claim, we can prove that the infection doesn't spread everywhere? So that would mean how many cells must be safe? Give me a lower bound on how many cells must be safe if not everybody's infected. 1. Could it only be one cell that's safe? No. Because if only one cell is safe, well then it would have to have all of its neighbors infected, and so it too would have to be infected. So I will not go into details, but I'll leave that to you to ponder. How many cells must be safe as soon as we know at least one cell is safe? The answer will actually improve itself. Okay, so now all we have to do is we have to just study how the perimeter grows. Or, I'm sorry, how the perimeter changes as we infect things. So we go through all the cases. Go through new infections. So one possibility is we could have had something like this, where these two walls were boundary walls of the infection, and this cell was not infected. What happens if we now infect this? So these two walls would be gone, and maybe we get these two, maybe we don't. It depends on what's going on around it. So for instance, I would need to know what's going on here. I don't have to, though. All that really matters is I'm trying to show the perimeter never goes up. If I'm in a case like this, I definitely lose these two walls as boundaries of the infection. And even if I gain these two as walls, there's no net change. So perimeter either the same or decreases by 2. And you can just go through all the cases like this. There's not that many configurations. Each configuration will have the perimeter either unchanged or decreasing. Interestingly, I think it will always decrease by an even number. What's the maximum number it could decrease by? 4. And so, if we had a situation like this, where we had these 4 infected, then we would lose those 4 walls. And as that new cell is infected, the perimeter would decrease by 4. So the perimeter is non-increasing. And since the perimeter starts off at most 4n minus 4, it can't get larger than 4n minus 4. Okay? So the monovariate is just an absolutely wonderful concept in terms of looking at problems. What do you think the difficulty is in implying monovariance? How many of you have ever seen this technique before? Why haven't you seen this technique before? This is a post-core 300 level math class. In Vulcan, we start doing this in grade school. Why don't you think this is done? What do you think is difficult about applying monovariance? There's got to be some challenge or we would be doing this more often. Yes? The claim that it only goes in one direction, so... So the difficulty is you've got to find something that will only change in one direction that's relevant to the problem. So here the perimeter is a nice thing. And if you come up with the idea of looking at the perimeter, then you're set. But that's the difficulty, is you've got to figure out what's a good thing. There's another concept lurking in this problem that will be useful in some of the stuff we do with fixed points later. And that's all the changes are by an even amount. 0, 2, 4, 6, 8. One of the easiest ways to prove something is non-zero is to prove that it's an odd integer. It's sad, but this is one of our most powerful proof techniques. You prove something is an odd integer, therefore it's not 0. We will use that numerous times. Okay. All right, any other questions about monovariance? So we'll keep this in mind for when we get to fixed point theorems. Did we do Newton's method in divide and conquer in this class? We did that earlier, right? And so the big thing when we did Newton's method in divide and conquer is that Newton's method just destroys divide and conquer. It's much, much better. Why do we still have divide and conquer? Yes? Not every function is differentiable. So it's not surprising that if we are willing to assume more about our function, we can get more out. The same is going to be true in our study of fixed points. If we are willing to assume a little bit more about our function, we can do more in terms of finding the fixed points or proving that the fixed points exist. So there will be 2 types of fixed point theorems. There will be existence theorems that say that we do have a fixed point, but we may not know where it is. And then there will be constructive fixed point theorems that actually give you a way to find the fixed point. Okay, so we're going to look at contraction x. So we'll have f from some space S to some space S. We'll have a metric D. So I'm assuming everybody has taken real analysis. If not, there's reviews of the concepts we need in the chapter, which you've, of course, all read for today. So we'll have some metric D. Frequently, we'll choose S to be some compact set. When we're thinking about our applications for operations research, it's not unreasonable to be assuming a compact set. We are not going to have infinitely many resources available to us. And we say a function f is a contraction if there exists a c less than 1 such that for all x, y in S, f of x minus f of y is strictly, well, I can do less than or equal to c times x minus y. So as soon as I write it like this, C now, I could have said C is positive, but writing it like this forces C to be positive. So what it's saying is if you take 2 points and apply f, let's say the 2 points started off over here, here's x, here's y, we apply f, here's f of x, and here's f of y. That when we apply our map, the 2 points get closer to each other. Okay?
And we're assuming S is compact.
Right now, I'm not assuming S is compact. In a lot of the applications, I will assume S is compact. I'm just saying I have a map where when I apply it, the 2 points are closer after I apply them when I start. Yes?
So by the absolute values, do you mean d of x?
Oh, sorry, yes. So d of xy, I will often write as x minus y. Thank you. Just as ease of notation. So the distance between the points in my metric. So for most of the time, we're going to use Euclidean spaces. We'll be using Rn. The important thing to note here is that this constant c is independent of x and y. How well does everybody remember real analysis? All right, I see at least 2 heads shaking positively. Excellent. What's the difference between continuous and uniformly continuous? This is like Guy Smiley, this is your life. Yes. It's 1 epsilon and?
Epsilon is a function of x.
I'm sorry?
Epsilon is a function of.
Well, I choose epsilon. I'm the evil person. I'm sorry? Well, the way it always works is for all epsilon greater than 0, someone gives you an epsilon, there exists a delta, you find the delta, such that, and this is what's going on at some point x. So functions continuous at x, I'll write the definition. Yeah, the height seems to have been screwed up by my colleague. I'll try it this way. All right. So it's continuous at x. Given epsilon greater than 0, there exists a delta such that for all y with x minus y less than delta, we have f of x minus f of y is less than epsilon. This is what it means to be continuous at x. What does it mean to be uniformly continuous?
That delta work for all.
Right. This delta is really some function of x and epsilon. Not surprisingly, if you give me a really big epsilon, I can probably take a pretty big delta. The smaller epsilon is, the smaller delta is. That makes sense in general. But it could also be the case that maybe the delta I take depends on x. So it's uniformly continuous if delta is just a function of epsilon. So you can use one delta everywhere. Okay? So when we go back to what we're doing with our fixed points, we have some c strictly less than 1 that works for all x and y. C is not allowed to depend on x or y. I can choose one c that works everywhere. Okay? How many of you have taken differential equations? Did you prove the existence uniqueness of solutions to first-order differential equations?
I think so.
Okay. Okay. Did you at least state the theorem? That if I give you a nice first-order differential equation, there is a solution in some neighborhood? Possibly? Maybe? So the question is, how do you prove results such as this? How do you prove that a differential equation has a solution? There's a lot of topics we could do in this class. This is not a class in differential equations, but there are notes in the book as to how you can use these fixed point theorems, how you can use these contraction maps to prove results in differential equations. So this is a really nice application of what we're doing. Anybody know the name of the method of iteration? Yeah. It's the wrong captain. Picard's iteration. Not a joke. Okay. But that's also why I'm not going to do it. So if you're interested, you'll read the book. I'm happy to chat about how you would apply this to prove certain differential equations have solutions. What I want to do is I want to prove a theorem about contraction maps. What kind of theorem do you think we'll be able to get? I'm sorry? Yeah, probably, since this is a lecture on fixed point theorems and we're starting off with all this stuff on contraction maps, that there is going to be a fixed point theorem result. So I will definitely have to have a conversation with my colleague about remembering the heights of things. All right. So we will prove that a contraction map has a fixed point theorem. All right. Yes?
I think I remember something in real analysis called Lipschitz continuous.
Yes. This is extremely similar to that. Extremely similar. And for a lot of things, we actually don't need functions to be differentiable. Some Lipschitz exponent is more than enough. And so one way to look at real analysis is it's giving us the language to prove things, and it's trying to figure out what's the weakest conditions we need for something to hold. So because you mentioned that, what does this kind of look like to you, since you've seen Lipschitz continuous? F of x minus f of y less than or equal to cx minus y.
Well, like the intuition is the slope is bounded.
Yeah, it's like the slope is bounded. If we divide both sides by x minus y and take the limit as y goes to x, this is looking a lot like the derivative at x. And so what this is saying is the derivative may not exist, but it's bounded in some range. And for a lot of applications, we don't need the derivative to exist. We just need the derivative. We just need some kind of control over the slope here. And so that's an outstanding observation. And for a lot of purposes, that will be more than enough for what we need. OK, so here's the theorem. Let's say S is compact. F is a continuous contraction map. Then F has a fixed point in S. There is a word that can be removed from this statement.
Single word.
Single word. Continuous. Why don't I need continuous? Ooh, that's horrible. Oh, absolutely horrible. Yes. So as soon as we know that it's a contraction map, We want f of x minus f of y to be less than epsilon if x minus y is less than delta. So if x minus y is less than delta, this is telling you how delta and epsilon should be related. If delta is less than epsilon over c, or something like that, we should be fine. Maybe epsilon over 2c to be safe. That will force f of x minus f of y to be small. So we actually don't need to say continuous. We can just say f is a contraction map. Okay? So what we're going to do is we're going to prove that there is a fixed point by finding it. How many fixed points do you think there are? So this theorem says it has a fixed point. What college football team do I root for? The Ohio State University. Right? Did not play well, but played well enough to win. Okay? Why is it not a Ohio State University? I'm sorry? There's only one. Right? For a lot of things in mathematics, we can have multiple things that have a given property. When you say this is the solution, there's no other solutions. This is a solution. There may or may not be other solutions. Do you think there could be two fixed points to a contraction map? Why not?
Because if there were, then it wouldn't satisfy the claim that they're getting closer.
Good. At most, one fixed point if it's a contraction. And the reason is, if f of x equals x and f of y equals y, then f of x minus f of y has to be strictly less than or equal to c x minus y, which is strictly less than x minus y, but this is just x minus y. And the only way this can hold is if x equals y. I'm sorry, this can't hold at all, sorry. So if I had two different points, impossible. So there's at most one fixed point. Okay? So if we can find a fixed point, we found all of them. So what we're going to do is we're going to construct a sequence of points that will converge to the fixed point. Anybody have an idea of what we should take for our first point?
0.
How do you know 0 is in the set? I'm telling you nothing about S. I will let you know that S is not empty. I'm sorry? We may not have an endpoint. Maybe our set S is the perimeter of a circle. Maybe it has no boundary. Well, we're assuming it's compact, so it should have a boundary. All right, so we're assuming it's closed. Could be, though, all of R. Did we assume compact? Okay. All right, so we've assumed compact, so we could take a point on the boundary. I think we could actually drop the compactness. But the point is, I'm not really telling you much about the space, right? So I'm not telling you much about the space. This tells you that we don't have that many possibilities for where we start. So proof. Choose any point. Take any point. What should we call that? Yes?
Just to clarify, so this proof is for S compact or S non-compact?
I think the proof will actually work even if S is not compact. In the cases we're going to look at, I don't think this proof requires compactness. But I will assume compactness right now just to cover myself. And then we'll see at the end if we actually need compactness. Choose any point. So we'll start off with x naught. That's our first point. We want to generate a sequence now. Any thoughts what the next point in the sequence should be?
F of x naught.
F of x naught. And we'll call that x1 is f of x naught. What's the next point? F of x1, which is f of x naught. And in general, xn plus 1 is f of xn. There's really nothing else we can do. Right? We don't know anything about the set. Maybe it has a boundary if I keep the word compact. And we have the function f to play with. Nothing else. So we can look at this chain. So how do you tell if a sequence converges? We could do the ratio test. If we're going to do that, we're going to need to know some things about. And if we're doing the ratio, we have to be careful. What if something is 0?
For a large n, the terms are close enough together.
Are close enough together. So what's the name of that criterion? Cauchy. The Cauchy, right? There's two main ways we know to prove something converges. One is to say, here's what it converges to, and show it goes to that. And then the other is, in certain spaces, if we can show that the distance between any 2 points is getting small as we go further down in the sequence, then it has to converge, yes?
Don't we need S to be complete for that?
So, yeah, so that we will need S to be complete. So what's the definition of a complete space? It's basically just taking the two sentences. Yes, I should not smile. So set or space is complete if every Cauchy sequence converges. Okay. I actually want to do things like this so we see why we're using the stuff we are from real analysis. Where do these things come from? Why do we care about these spaces? Right? The space Rn is going to be complete. We're not going to worry about that. So what does it mean to be Cauchy? I know it's been a while since some of you have done real analysis. Yes?
For n and m, there is some like capital N.
Okay.
Such that if like lowercase n and lowercase m are greater than capital N, they're epsilon close to f.
Okay. So we got to phrase it right. Given epsilon greater than 0, there exists a capital N, which is a function of epsilon, such that now for all nm greater than or equal to n, xn minus xm is less than epsilon. So this is what it means to be a Cauchy sequence. And a complete set, a complete space, is a space where all Cauchy sequences converge to. So this definition is a little incomplete. To a point in itself converges to a point in that space. It's not enough to converge. I want to converge to something in that space. Okay? So again, I'm not sure how your real analysis class was taught as to the motivation behind results like this. So just in case there wasn't some motivation, this is where it's coming from. And as we start to try to prove the result, what do we need to make the proof work? If we're trying to show that there's a fixed point, we want that fixed point to be in the initial space. Right? Otherwise, if it's not where f is defined, it does us no good. It's not a fixed point. So it's clear that converging to something in that space is going to be extremely useful. Now the ratio test is going to be close to what we're going to use. We're actually going to be using, I think, closer to the comparison test. All of these are really the same. The way you prove the ratio test and the root test is comparison test with an appropriate sequence. So, armed with all this stuff, now we should be able to do the proof. So, proof of theorem, really. All right. So let's look at xn minus xm. And we want to see how close this is. Okay? Without loss of generality, let's assume n is greater than m. Comes later in the alphabet. How do we want to look at the distance from xn to xm?
Well, to get from one to the other, you're applying f, the difference of n and m times, right?
Right, but just to one of them. So once we have xm, we apply f something like n minus m more times to get to here. What would you love m to be? N minus 1. So let's do the special case when m equals n minus 1. If this is the case, then this is f of xn minus 1 minus f of xn minus 2, which is less than or equal to c times xn minus 1 minus xn minus 2. Right? So if they were right next to each other, we would now get it's less than c times this distance. What if this was xn minus 2? How might we look at this difference? Is there a thought? A triangle inequality. Yes. Triangles are good. What would you want to do the triangle inequality with? What point? So let's look at xn minus 1 plus xn minus 1 minus xn minus 2. So we do nothing. We do nothing by adding 0. And now this would be less than or equal to xn minus 1 plus xn minus 1 minus xn minus 2. And so we could then apply things again to this and get this in terms of xn minus 1 minus xn minus 2. Right? So this would become less than or equal to, I think, c plus 1 xn minus 1 minus xn minus 2. And if we had more, we would have c squared plus c plus 1, c cubed plus c squared plus c plus 1. And now we can begin to see why we might want something to be compact. So I'm going to stop here and let you think about whether or not we actually need it to be compact. We will resolve that question on Wednesday. Okay? Please grab some more candy on the way out.